Okay, so let's continue from last time, right? So far I've discussed causal inference as two parts, right? So one part is causal effect, learning causal effect. For example, macroeconomics, there's a bunch of theory, right? So the market, there's partial equilibrium, general equilibrium, in all kinds of market you study. When you study international trade theory, there's labor market, labor theory, there's industrial organization theory, there's game theory, right? There's all these theories that you study in different classes. But then when you go and do econometrics, so when you go and touch data, do you use them? That's the question. Do you use the theory that you have learned in economic theory class when you do econometric analysis? Right? Do you use the demand and supply? Do you use your Heckscher-Ohlin? Do you use your game theory? Do you use these theories when you try to do estimation? Almost never, right? Almost never. Okay? So when you do econometrics, it's like you're just dealing with statistics and a little bit causal inference, but we're not really directly using any theory that you have learned in other economic classes. So it's like the two are completely separate, right? Well, this approach has been called reduced form approach in economics. So the reduced form approach is doing causal inference without explicitly using the economic theory to design the functional, like design the statistical model that you're using, right? So it turns out that this is not the only way. So in economics, there has long been applied economic research. There has long been two camps that battle with each other. So one camp is called reduced form. The other camp is called the structural. Now, the reduced form camp basically rely on statistical model to do causal inference, to identify treatment effects or causal effects. Okay? So reduced form uses statistical models. And the way that reduced form does it, traditionally, is the way that I've been presenting, which is, using reduced form approach still relies on theory, right? We still use theory, but we don't use theory explicitly. We use theory to establish what variable we want to control, right? What is our design, right? So the theory is used to achieve identification, but it's not used as a model. So the statistical model, so the model we use in reduced form approach is a pure statistical model. Okay? Something like y is equal to beta 0 plus beta 1, x plus e. That's a reduced, right? So the statistical model like this is using the reduced form approach to estimate the causal effects that we're interested in. Right? There's no theory. Theory is only used when we're trying to achieve identification in the first stage. But when it comes to the second stage, we rely on the statistical model. However, that's not the only approach. Okay? There is also another approach called a structural approach, where we treat theory very seriously. We completely believe in theory, so that we use theory to specify a model. Okay, so the structural approach estimates a theoretical model, not a statistical model. Okay? So the difference between the statistical model versus theoretical model. So this you can think about in that sense. Right. Now, I'll give you an example. Okay? Suppose you're interested in education, right? On wage, again. Okay, so the effect of education on your wage is a classic causal inference problem. So you can run a regression like that, and then you can control, right? So you can control for things you want to control. For example, you can say, I want to control for something that proxies for my ability. Right? For example, like test scores and stuff like that. Right? So you can add variables that control for ability, for example. So the identification argument is that there is ability, okay? And then ability can lead to wage, it can lead to education, can lead to wage, etc. Right? So there's an underlying theory, and based on the theory, you say once I control for this, this equation give me the causal effect. So we're estimating this statistical model in the end, right? But think about what is the economic theory? What economic theory say about the relation between education and wage? In particular, suppose we're talking about college education, right? Whether somebody goes to college, has a college education, what does economic theory say about college education and the wage that college-educated people earn? What is the economic theory between, like, what is the economic theoretical link between the two? Well, there are many, many models, right? There are many theoretical models, but the simplest theoretical model says the wage of college versus non-college, the so-called college premium, is determined by a basic supply and demand, right? Very simple, okay? There's a supply of college students, and there's a demand for college students relative to non-college. And the equilibrium will be the wage earned by the college students, okay? And of course, there's another separate market. We can talk about separate market for non-college educated students, so that the wage will be give you the premium. So right. So economic theory says everything is determined in a market where there's supply and there's demand, and the wage is the equilibrium. Okay. Right. Okay. So if we treat this theory seriously, then there are several things we can say. Right. The first is I can estimate the supply curve from data. I can estimate the demand curve from data, and the equilibrium gave me the observed wage. That's the structural approach. Okay, the structural approach treats economic theory very seriously. And it says, okay, I believe that the observed wage, the wage I observe, is actually the equilibrium wage. So I use the data to estimate the supply curve. I use the data to estimate the demand curve. And then I'm done. Okay, and then this is my estimate model. And using this estimate model, I can do a lot of things. For example, what is the treatment effect? Right? What is the treatment effect of going to college? Well, suppose this is the market for college students, and I can do the same for the market of non-college students, right? And then the difference between the wage should be the beta, okay? Should be the treatment effect of going to college. But I do not do this statistical model. I estimate the supply and demand for college. I estimate the supply and demand for non-college, and then the difference tells me the treatment effect. Okay, so this is sort of like the structural, in a nutshell, this is sort of like the structural approach to estimate this kind of problems. All right, now this is the first thing. The second thing that, if you compare the difference between them, if you think about economic theory, it should be obvious to you immediately that the reduced form approach has significant limitations. For example, what does this beta 1 mean? This beta 1 means the treatment effect of college on wage, right? But what is the treatment effect of college on wage? That means if you go to college, how much additional money you earn. But this thing is an equilibrium complex. So if we think about theory closely, that we know that the effect of going to college is equilibrium outcome. Okay? It depends on what? It depends on the supply of college people. It depends on demand, right? So for example, if this is 2010, if this is 2019, we have in China there's this amount of people go to college, and there's this amount of demand for college students. Then we have this equilibrium wage. From this equilibrium wage, we can get a treatment effect. But tomorrow, what about next year? Suppose next year more people go to college like this. Okay? Supply curve goes down, then we will have a lower wage, right? And then we have a lower premium. In other words, the treatment effect of college depends on what? Depends on how many people go to college, and depends on the demand for college students. It's an equilibrium outcome. It's not something like, so this beta is not fixed. It's not universal. It's not fixed. It is the outcome of market equilibrium. Whenever market condition changes, this thing changes. When you do reduced form estimation like this, right, how do you interpret the beta you get? You're often not very sure about this. Because, does this beta apply this year? Or does this beta apply next year? Does this beta apply in other countries? You typically have very little idea. Because why? Because this beta actually is in equilibrium and depend on the underlying supply and demand. So if we do the structural approach, and we estimate the supply curve, estimate the demand curve, then we are able to predict what happens to the college premium when more people go to college, for example. We're able to predict that. But using the reduced form approach, you will not be able to do that. Right? So I hope this is clear to you. Okay? So the reduced form approach, by ignoring the fact that this is an equilibrium outcome, has actually more limited to say about the true mechanism of what's going on. Right? The structural approach, on the other hand, shows very clear. Okay? Just thinking in China, for example, we had a very large college expansion, right? like 10 years ago or something. So there's a huge increase in the number of students with a college degree. And as a result, of course, as many papers show, that the college premium actually decreased. Right? So this is very obvious. When more people go to college, supply growth goes this way, the premium will decrease. In order to capture that effect, the structural approach will be able to do that, because we estimate the underlying supply and demand. While the reduced form, it's harder to do. Right? You have to think more clearly and design a model. Okay? So this is sort of the idea behind the structural approach, which is treating theory seriously, and then back out the theory from the data, and use that estimated model to do predictions. Now, it turns out that the structural approach is actually probably older in a sense, in one sense, because when econometrics was first when economics was first sort of invented, in a sense, it began as a structural approach. Okay, so econometrics began as a discipline that tried to link economic theory to data. Economic theory features very importantly in the beginning, in the founding of econometrics. All right. So this is the Econometric Society was founded in 1930. And it's actually founded during a gathering of the American Economic Association and the American Statistical Association. Ragnar Frisch was a founding member of Econometric Society and the first editor-in-chief of Econometrica, wrote this in 1923. He says, intermediate between mathematics, statistics, and economics, we're going to find a new discipline, which, for lack of a better word, let me call it econometrics. Okay, so that's what he does. I'm going to call it econometrics. Econometrics has its aim to subject abstract laws of theoretical economy or pure economics to experimental and numerical verification. So what he's saying here is the goal of the econometrics is to test. Okay, is to test economic theory with data. Right, apply economic theory to data and test economic theory with data or experimentation. Right. And later on, he wrote, so far we have been unable to find a better word than econometrics. We are aware of the fact that in the beginning somebody might interpret the word to mean economic statistics, but it's actually not economic statistics, right? Because we believe that it will soon be clear that our society is interested in economic theory just as much as anything else. So what he's saying here is economic theory is extremely important to econometrics. At least that's his vision, or at least the vision of the Econometric Society when the society was first founded. All right. Okay. Today's, the beginning of econometrics is closely linked with the Coase Foundation. The Coase Foundation established in 1932, where it's one of the earliest efforts to do econometrics. And the Coase Foundation always has this motto, which is theory and a measurement. All right. So theory again features very prominently in the founding of econometrics as a discipline. Today, however, right? Hey, that's very good. Love the music. Okay, so in summary, so this is what Hood and Kuhlman wrote. In summary, econometrics was conceived at the very beginning as a branch of economics in which economic theory and a statistical method are fused together in the analysis of data. Okay, so today econometrics is very different. Okay, so the way that econometrics was done today is kind of different from the way it was founded in the very beginning. Right? So today, like I said, we have reduced form and a structural. We really have two camps, and they're completely separate from each other. And in fact, they do better with each other because one camp says I'm the better one, the other camp says I'm the better method. Right? So they actually better with each other. So today we say. If we are estimating causal models based on economic theory, then we call it structural model. And if we actually estimate a model from data, we call it structural estimation. So the structural estimation today refers to the practice of treating theory seriously and try to estimate the theory from the data. Okay, so that's called structural estimation. Now, I'm going to give you some example, right? So I already said something about the wage example, okay? Education and the wage. Let me give you a slightly more complicated example. Okay? So this is an example of auction. All right. So I think I showed you something in the introduction, but let me walk through it more closely now. Suppose I have the following data, right? The number of bidders and the winning bid. So we have a bunch of first prize seal bid auction. How many of you have studied this model in game theory class? Anybody? Because you should game theory should teach you this auction model, no? Okay, all right. So I see somebody even nodding, right? Auction is a typical example where we have pretty good game theoretical model to describe, all right? Now, in a sealed bid first prize auction, everybody put their bid in a sealed envelope, and then put and then submit it. And the auctioneer opens the envelope. Whoever bids the highest wins the bid. Okay, wins the item. And the first prize means whoever bids the highest price pays that price and gets the item. All right. So if we run the same first prize sealed bid auction of the same kind of thing for many times, we kind of see this kind of data. Where if the auction has more people participating, and then typically we will see a higher winning bid, even though we are auctioning the same object, same type of object. The more people participate, the higher the winning bid that is. All right. So, what is the goal I'm trying to do here? Suppose I'm trying to I'm interested in predicting the winning bid, conditional on the number of participants. I want to know, suppose I'm the organizer of auction. I want to know what if I have like 30 people participating? What is my expected winning bid? I'm interested in that question. There are two ways to do it. The first way is just fit a statistical model. Okay, let's just fit a statistical model. For example, this one is a linear model. Okay? Linear regression. Number of bidders here, winning bid here. I can do that, right? Now the linear model doesn't seem to, maybe it looks pretty okay, right? So here's the data. The linear model looks okay, but I can also do a quadratic model, right? A quadratic model is this green line. It also looks that it fits the data pretty good, right? Okay. However, right, this is the first approach, which is using a statistical model to fit it. What is the second approach? The second approach is to think about, in economic theory, think about what is happening here. Why do we see a higher winning bid when there are more people participate? What is the underlying mechanism? How do we use economic theory to describe what is going on here, right? Now, to that approach, we can think about a game theory model. Right? So this is a game theory model where we imagine that all the people who participate are, first of all, risk-neutral bidders. They all have some underlying value of how much do I value the object, and then every bidder knows their own value, but do not know the value of other people. Okay, but they kind of know the distribution of the value. That's the assumption. So if I don't know other people's value, but I kind of know their distribution, then I can design my optimal bid. So how do I design my optimal bid? Well, very easy. Okay, so what I'm going to do is I'm going to choose a bid to maximize my V. So this is how much I value the object. This is my bid, right? Now, if I win the auction, this is how much I get. My profit is my value minus my bid. But only if I win the auction. So probability times the probability that I actually win the auction, which is my B. My bid is larger than all the other bids, okay? So all the other, let me just write a B minus me, okay? Right. So, everybody else up there. So my bid is let me just say my bid is the maximum. Okay? Now, if I know something about the distribution of other people's value, then actually I can solve for my optimal bid strategy, right? Actually, this is the strategy. Okay, my bid should be my value minus this complicated looking function, right? Okay. So if we describe this auction using this game theory model, then everybody's bid will be their value minus something, okay? Which is this complicated integral. That's their optimal strategy. Right. Okay. So I can use this model, game theory model, to describe the data, right? If we treat this model seriously, then there is a way for me, because if I treat this model seriously, then I would say the winning bid I observe here or the bit I actually observe are the optimal bit that people submit based on this strategy. So if I believe in this model, then from the observed bit, I can identify or I can estimate their actual true value. Okay? So that's strategy. Right? Once you believe in the model, then from the observed B, we can try to estimate the V. Right? So that's exactly what I'm going to do. All right? I'm going to estimate the V from the observed B. And using the estimated V, I can predict what's going to be the winning bit if more people participate. Right? Because now I know everybody's V. And then I know everybody, and I know the distribution of V. So once I know the distribution of V, I can predict if there are 50 people participating or if there are 100 people participating, what is going to be likely, likely going to be the winning bit. Because now I've estimated the distribution of bit, and I know their bidding strategy, and from that, I can always predict the winning bit. Okay? So this is the result, all right? The result is this red line, which I call model. Okay? So this red line is my prediction after doing the so-called structural estimation, where I treat the model seriously, and then use the model to help me estimate the underlying V, and then use the underlying V to predict the winning B. Okay? Now, if you're interested in how exactly to do that, you can take a look at this paper because the methodology comes from this paper, what I described here, which is Gao and Wang Huang 2000 econometric paper, which is one of the first really nice paper that estimates auction using a structural approach. Okay? All right. So let's take a look, right? This red line is my prediction from a theoretical model. And when I treat the model seriously, this is my prediction. So how good is this theoretical model? Well, just simply looking at the data, right? Do you clearly see this model outperforming the statistical model? Do you clearly see that? Maybe not. In particular, let's take a look at this quadratic one, right? This green line. This green line looks very much like the red line. So it looks like, doing this very complicated theoretical prediction doesn't really give me too much over the statistical, very easy, very simple statistical fit, right? Okay? However, what if I actually increase the number of bit? So in other words, what if I want to predict, because this is what? This is like the in-sample, in-range prediction. Now what I'm going to do is I'm going to try to predict what happens when I have, let's say, 30 bidders or 50 bidders. So when a number of bidders goes out of this range, goes out of the observed range of the data. Now in that case, we have this relation. Okay? This is happens when we try to predict out of the range of the original data. Right? So let's go beyond 25, from 25 to 50. Now, this is the model prediction. So this is the true data according to our simulation. And this is our model prediction. This is the statistical prediction of quadratic. This is the statistical prediction of the linear. You can immediately see that the statistical prediction becomes much worse once we go out of range. Okay, in range, they're pretty good. The quadratic looks okay. But once we go out of range, it becomes extremely bad. While the model prediction, the theoretical prediction, is going to give us the correct answer. Right? So, what is happening here, right? What is happening? Well, what's happening is this. First of all, why does the statistical model behave very badly once we go out of range? Do you have an idea why? The reason is very simple. In the first half of the class, we talk about all kinds of machine learning methods, right? But whatever method you use, it's going to do this or this. Okay? Why? Because any method, any statistical model, you can try to find, or whatever you use, you can use very complicated, very powerful statistical models, state-of-the-art machine learning and deep learning models. It's not going to solve one problem, which is any model can only try to find the pattern on which the data come from. Okay, so suppose you say xi, yi, and this is your data, and this data come from the underlying population of xy, right? So there's underlying population, joint distribution xy. So using a better statistical model just means finding a better pattern that describes this population. Okay, this population. But the model will have basically no power to predict if the population changes. Right? So if this is the population and I have new data coming from this population, then I can use my model to predict. But once the population changes to something that looks differently, then statistical model will lose their power to predict, very obviously, because my model is trained on this population, right? So what happens here is very simple. The population changes. Once we go out of range, the joint distribution between x and y changes to something different from the disjoint distribution here, right? Very clear, okay? You can take a look, right? The joint distribution obviously is different. So any statistical model trained on this population will have a pretty hard time, very hard time, trying to predict the relation in this new population or this new joint distribution. Okay? There's no power to predict. But why does theory work? Well, because the data is generated from the theory, right? So in this particular example, the data is generated from, our theory is the correct theory. The data is actually generated from the theory. So of course the theory is going to predict very well. But in general, the reason why structural estimation works in this kind of situation is because our theory has described, if our theory describes the underlying mechanism of why the data is generated, then the theory will be quite useful to go out of range. Because once we go out of range from this population to this population, the mechanism is not changing. Okay? Right. The statistical distribution has changed. If you look at this half and this half, the underlying statistical distribution is different between x and y. So any statistical model trained here will have a very hard time to do prediction here because the distribution has changed. However, the underlying mechanism is not changing. So if I have a good theory that successfully describes the underlying mechanism, and I can estimate that theory, then the theory will be a very good guide to help us predicting this range. So that's the underlying idea. All right? Now, if you remember, at the very beginning of this lecture, let's see, I have made one point which is related to this. Remember this example, Simpson's paradox, right? The idea of Simpson's paradox is that the correlation, right? The idea is the correlation between x and y, right, is negative or positive. I forgot, but I think it's negative if we look at the entire sample. But if we condition, right, if we condition on some other variable like z, so in this case, if we condition on gender, then the correlation becomes positive. But you never know, because you may condition on some other things, right? You can condition not only on gender, but you can also condition on height. And if you condition on height, maybe the correlation becomes negative again, right? And you can condition, whatever you do. The point I'm making here is the Simpson's paradox tells one thing, which is any statistical relationship between two variables, okay, is highly unstable. Okay? The population can easily change. The distribution can easily change. So statistical relationship is unstable. That's the point I'm making. What is stable is causal relation. Causal relation and causal mechanism tends to be much more stable than statistical relationship. Because statistical relationship is correlation, and correlation can be reversed very easily. You condition on something, it can reverse. Condition on some other thing, it can reverse back. So statistical relation is very unstable, whereas causal mechanism is much more stable. And that is the idea behind what we are doing here, all right? Okay. That's the idea exactly behind this. My theoretical model captures the underlying stable mechanism. And for that, because of that, I can use it to do out-of-range prediction where the distribution has actually changed. Okay? Statistical distribution is unstable. You put it here, that's one distribution. You look at here, that's another distribution. You combine them, that's a different distribution. So if you focus on estimating statistical distribution, your result tend to be lack of what? lack of what we call external validity. I remember this concept, right? I've already talked about that. Okay? All right. So this is one example, right? So the auction example. There are more examples. And after this example, I'm going to make some more general points. But this example of monopoly, right? So another very good example of taking a look at the power of structural estimation. So suppose we have a bunch of different markets. Every market, people have, there's some high-income market, medium-income market, low-income market, right? So the data we see is price, sales, average income of different markets, the population of different markets. If we put them on a single graph, we can say, okay, here's the sales as a percentage of population, divided by population. This is the price, and we can plot all the markets together. Now, we assume that these data come from the sales of a monopoly firm. Right? So a big firm that dominates the market, and in different market, it charges a different price, and it has different sales. Okay? All right. So, what can we learn from this data? All right. Now, first of all, if we simply fit a statistical model, or if we do the reduced form approach, where we study the relation between different variables causally, what can we do? There's not much we can do. We can run regressions. We can run a regression with Q, sales on the left-hand side, maybe P on the right-hand side, right? And then we can maybe control for income, and we can run a regression like that. Okay, I don't know what that tells me, but we can do reduced form regression like this to discover the relation between different variables, or maybe even causal relation between different variables. So that's one thing we can do. But I can also try to think about what is the mechanism that generates this data. And I use a structural model to estimate the data. Okay, so how am I going to do this? Well, in theory, economic theory tells us how monopoly prices things. Now, I think you have all studied industrial organization, right? Very simple IO model. How does monopoly pricing? Right? How does monopoly do pricing? Extremely easy. Monopoly maximize. Suppose I have a demand curve. So suppose this is let M be the market, right? Market M, and for market M, suppose I have a demand curve which is Q as a function. Demand curve is QM as a function of P, right? Which is a demand curve. Okay. So based on this demand curve, how does the monopoly choose the best price for that market? Well, it maximizes price times quantity minus the cost, right? Very simple, okay? So this cost is a function of Q. The more you produce, typically the higher the cost, and the monopoly will maximize that. If we use a graph, I'm sure you have all learned this in introduction to economics. So if this is the demand curve, this is the cost function, marginal cost function, then you can derive the marginal revenue, then this is going to be the optimal price, this is the quantity, okay? Right? You're all familiar with this IO model. So what I'm going to do now is I'm going to treat this theory very, very seriously. I'm going to say the P and the Q is exactly the P and the Q I see here. Okay? So I'm going to say the P, the price and the sales I observe from the data is exactly the optimal pricing and the optimal quantity I can derive from my theory. So in doing so, I'm treating the theory very, very seriously. Right? Now, let's take a look at the implication of this. If I choose an optimal P to maximize this model, what is the solution? The solution is this, right? People familiar with this? The learner index and optimal pricing for monopoly. The marginal cost is equivalent to the price plus plus the derivative Q as a derivative dQ dP times Q, right? Plus P is equal to my marginal cost, right? So this is the monopoly pricing formula. Actually, another way to write it is P minus MC divided by P is 1 over elasticity, right? Demand elasticity. This is the learner index, okay? People familiar with that. Okay, so if I treat this very, very seriously, then I can use this relationship to very quickly find out what is the marginal cost of this company, right? Because I see the P from data. So I already know this P, okay? If there's a way for me to also estimate the demand curve, which is, at each market, how much do people demand based on a certain price, I can also get this from data, because the data tells me in each market how much do people buy if the condition on a certain price. So I can also estimate the demand curve from data. So based on the demand curve and based on the observed P, I can estimate the marginal cost of this company if I treat this theory seriously. Okay? Do people follow me here? Right? Now, if I'm not going to go into too much detail, but if you're interested, you can read my description of how we estimate the demand. It's not difficult. We can estimate the demand curve for each market, and then I'm going to treat this equation very seriously, and then say the marginal cost of this company is exactly equal to the observed price plus this term. Okay, you can derive from the demand curve. Now, if I do that, then what if I do that, then I can estimate the marginal cost of this entire company. Okay, so this will be my estimated marginal cost. Now, in this graph, what I'm plotting is my estimated marginal cost and the estimated demand curve of a single market, because I have many markets. I pick one of the market, I plot the estimated demand curve, and I also plot my estimated marginal cost curve. All right. So this is how the market. So this is how the monopoly this determines the optimal pricing. This is the quantity that the monopoly actually sells in that market, which is exactly the textbook, right? This is exactly the picture you will see in any textbook talking about monopoly pricing. This is the demand curve. This is the cost curve. The optimal quantity is here. The price is here. What is this area? What is this triangle? The dead weight loss. Right? So from this picture, you can even calculate dead weight loss. Okay. So this is what theory can tell me. Right? Let's go back and think about it. Simply from this data, there's price, there's sales, and there's income of all the markets. Can you get cost information if you're not using theory? There's no way, right? Without using economic theory, there's no way for you to guess what is the cost of this company, because our information only has price and sales, and also income. But using economic theory, I can estimate the cost of the company, which is very powerful. Because once I have the cost, I can do a lot of things with this. I can do a lot of things. I can make a lot of different predictions. Right? The first thing I can do is I can do welfare analysis, which you will never be able to do if you're doing reduced form or if you're doing statistical, right? The welfare analysis, how much dead weight loss is this company causing the market? Are you able to do it without using theory? No way. Actually, the whole concept of welfare is a theoretical concept. So without using theory, there's no way for you to do that, right? Okay. So the first thing we can do using a theoretical model is we can use it to do welfare analysis and also make normative statements. Right? That's the power of structural model. Now, the second thing we can use, once we have this cost function, the second thing we can do is we can do something called counterfactual simulation. So the counterfactual simulation means I want to predict what happens if something never, in reality, never happened before. I'm going to predict, right? I'm going to predict the effect of a treatment that has never happened in my data. Right? Is reduced form able to do that? No. Right? So remember, when we discussed causal effect learning, I said if I want to know EY given do X, right? Now what do we need? Well, when I was talking about that, I said, okay, you need data on X, Y, at least, right? You need data on X, you need data on Y, and then maybe you need data on some W that blocks the backdoor blocks all the backdoor path, etc. If you don't have W, you find something that the front door or the IV, right, etc., etc. Okay, so that's what we said. But in all this discussion, we have assumed that at least I have data on X, which is the treatment. But what if I don't even have data on X? I never have data on the treatment. Can I still predict this one? Yes, if you use a theoretical model, right? So structural estimation has the ability to predict this effect without any data on X. Why? How? By estimating the underlying mechanism, and using the underlying mechanism, we can try to predict what this happens when something that has never happened before happens. As an example, okay? Let's try to do this. What if, what happens, I see this market, this monopoly of many different markets pricing sales data, right? I'm going to try to predict what happens if the government imposes a 20% sales tax on Hong Kong, right? So there's no sales tax in the data. So the sales tax is a treatment that has never observed in the data, okay? Never happened. But I'm going to predict what happens to price, to quantity in all different markets when the government does sales tax, okay? T equal to 20%. Are you able to do this without using theoretical model? There's no way. But can you use theoretical model to do this? Yes. How? Very simple, okay? What happens when the government does a 20% sales tax? The marginal revenue goes down, right? It's really that simple, okay? So I know this is the demand curve. This is the marginal revenue curve. This is the MC. Given the marginal revenue, I have the optimal price and the optimal quantity. So when the 20% tax happens on this market, simply the marginal revenue goes down. So now I have a new different pricing, right? New different optimal pricing. And also actually a new quantity and new pricing. Once I have information on marginal cost, I can predict everything. I can predict what happens with the 20% tax. I can predict what happens if the government maybe gives a 20% subsidy that lowers the cost. I can do all kinds of prediction. Because why? Because I already have the underlying cost estimated. And using that, and using economic theory, I can do this kind of prediction. Predicting the effects of treatment that has never happened in reality. Okay, so that's called counterfactual simulation. And only structural estimation has the ability to produce counterfactual simulation. If you're using reduced form or any statistical model, there's no way to do that. So I hope I'm convincing you, right, on this virtue of structural estimation here, right? Okay, so here is a classical poem on counterfactual simulation. Or not that counterfactual, right? Everybody know this poem, right? By Robert Frost, The Road Not Taken, right? Basically, the author says, one morning I go on a walk, and there are two divergent roads, and I took one, and I walk and walk and walk, and I'm never able to go to the other one. So after I finish my walk, I keep thinking about what would happen if I had taken the other road. Okay, so this has often been interpreted as a poem that reflects on the on the fact that in life we have many divergent paths, and once you pick one, there's no way back, right? That's always being reflected. So they interpret it as an analogy on life. But here I'm going to interpret it as an analogy on counterfactual simulation, right? So in reality, what you see is people taking one road, but I want to predict what happens if the person has taken another road before, or I just want to predict what happens if something never happened, in my data happens. So that's called counterfactual simulation. And using structural model, you can do this. Without using structural model, there's no way to do that, right? Okay. All right. Okay, so going back, let's summarize a little bit, right? What does structural model do? And why is it different from reduced form? Okay. Well, first of all, structural model estimates mechanism. Okay. And the mechanism is specified by the economic theory. Right? Now, so this is what structural model does. The mechanism is specified by theory. So what is the difference between structural and reduced form? Well, the question here is, so structural model uses economic theory. Does reduced form use economic theory or not? Does reduced form use economic theory? That's the question. Well, the answer is yes. Okay, reduced form also uses economic theory, but in a different way. Okay? The way that reduced form uses economic theory is the way that I have talked about in my previous lectures, which is this. Suppose I have a variable x, I have a variable y, and maybe there's some kind of z, and maybe there's some kind of w, right? There are some causal relation between them. The mechanism that binds them together is maybe z goes to x, z goes to y, x goes to w, y goes to w. Okay? Suppose. So when I draw this causal graph, I am not giving any functional form to the relationship. I'm simply saying this causes this causes this, and these two cause that. There's no functional form assumptions. Okay? Now, based on this graph, I can say, okay, if I want to know the causal effect of x on y, then I need to control for z. So I need to estimate x. So I need to estimate y, conditional on x and z, right? Okay? Because if I condition for z, then the correlation becomes causation, etc., etc. So that's my first stage. The second stage is let's pick a statistical model to describe this object. So what is this statistical model we pick? It can be anything. Can be this is equal to beta 0 plus beta 1x plus beta 2z. Okay? So this is a sort of like a typical reduced form approach where we use this causal, we use the theory. This is basic theory, right? Okay? This is our theory. So I use this theory to think about what I need to estimate. So I use the theory to transform causal objects into a statistical object. And I'm going to pick a statistical model to try to estimate this statistical object from the data. So this is like a typical reduced form way, which we have discussed for a long time in our previous lectures. But what is structural estimation does? Well, structural estimation also uses theory, but then the theory is not only a graph. The theory actually gives detailed functional form of what these links look like. So now, in that sense, what is the economic theory? Economic theory, or any scientific theory, actually specifies the functional form of x, y, z, w. Okay, do people understand? So any theory is economic theory or physics theory or any scientific theory is not just a graph that says which one causes which, but also gives the functional form of how these variables actually, using mathematical functional form to describe their relationship, right? Which gives an f function that describes the joint relation between these variables. And what structural estimation does is treating this functional form specified by the theory very, very seriously, and then estimate all the parameters in this functional form according to the theory, and then use the estimated f to do all kinds of prediction, like counterfactual simulation. Okay, counterfactual prediction. So that is really the difference between them. Okay, both approach use theory, but reduced form only use theory to do identification. Okay, to think about how to transform causal into statistical. Structural approach treats theory very seriously to the point that we believe all the functional form assumptions. And then we estimate the entire function and then use it for prediction purposes. All right? Okay? Now, so this is the first difference between the two. Okay? So one gives the structural model gives functional form to the causal model, and reduced form does not rely on functional form to the model. The reduced form approach chooses a statistical model to fit the relationship rather than relying on theory to specify functional form. Right? So that's the first difference between the two. The second difference between the two is the reduced form approach is typically a discriminative method, while the structural approach is typically a generative method. What do I mean by discriminative versus generative? This is actually a very essential difference between the two. Now, remember back in the days, okay, in the very beginning of this semester, when we were talking about the foundation of statistical learning, I said in statistics there are two different kinds of approach. One is called discriminative approach, the other is called a generative approach. I'm not sure if you remember that, but the discriminative approach, so give you x and y, okay? Given x, y. The discriminative approach is try to estimate the distribution of y conditional on x, or ey given x. This is called a discriminative approach, which is given x, let's try to predict y. Okay? Discriminative. Now, what about generative? What is generative? Do people remember what generative means in statistics? Generative means I'm now trying to estimate py given x. I'm trying to estimate, very good, okay, px. So I'm trying to estimate the entire joint distribution. The difference between them, so why do we want to do generative? Now, if my goal is only to predict y, given x, then maybe I do not need to do generative. But there is a singular advantage of doing generative, which is once I have the joint distribution, I can do simulations. I can simulate new data. Now, can I simulate new data using discriminative models? Well, the discriminative models, suppose I have estimated this model, right? Then if I give you x, say x equal to, so there's no way to generate new x data, because we do not know the distribution of x. We only know the distribution of y conditional on x. So using the discriminative model, I will never be able to generate new x data. I can only what? I can only give you x and try to generate a new y data, right? Because I have this one. So if I give you x equal to 4, then I can use this information to generate new y data, conditional on x. But I'm never able to generate new x data because I don't know the distribution of x. But for the generative model, I can, once I have estimated, then I can use it to generate all kinds of new data from the underlying, like from this distribution, right? So in other words, doing simulation and generating what is called a synthetic data, okay, fake data or synthetic data, is a specialty of generative model. Now, what does this remind you? Well, it should remind you of the counterfactual simulation we were just talking about. It turns out that another major difference between structural and reduced form is that reduced form method is typically discriminative, while structural is typically a generative method. So once you have estimated the structural model, you can simulate new data. And that's the power, that's why it can be used to do counterfactual simulation. Okay? Right? Now, example? Example would be, in the case of auction, for example, right? The reduced form approach is give you the number of bidder, let's try to predict the winning bid. But the structural method is trying to predict the underlying, like the entire model. So the entire model says, okay, what is the underlying value of people? Let's estimate those values. Now, once I have estimated those values, I can use these values to generate all kinds of new data that never happened here. Okay? So, for example, I can say, let's go out of, let's have 50 bidders. But not only that, I can do more fancy stuff. Once I have estimated V, there are many things I can do. For example, we're talking about what? We're talking about first price seal bid. What if I want to predict what happens when I have a second price seal bid? Do people know what second price, right? Second price auction is the winning person only pays the second highest bid. Now, can I predict the winning bid once, based on this data? If I only have data from first price auction, can I use the data to predict what happens when we have a second price auction? Not using reduced form, okay? Because reduced form only allows you to predict winning bid conditional on the number of bidders in this environment. But if I have estimated the underlying value distribution of people, then yes, because my game theoretical model will predict what happens when I do second price. Okay? So the structural model is like a generative model. Once I have estimated, I can use it to simulate new data in environment that perhaps never happened before, right? So the same thing applies to this. The same situation applies to this kind of data, right? Once I have estimated the underlying cost C curve, then I can use it to simulate new P and a new Q. New P, Q, if there's a taxation, if there's a subsidy, whatever it is, right? So, in summary, here is the way I like to write it. In statistics, we have discriminative model and a generative model. And the discrete model is py given px. Okay, py given condition x. A general model is joint distribution of pxy. Okay. Now, in causal inference, we have a similar generative versus discriminative difference. In causal inference, a discriminative causal learning, which is a reduced form approach, is we're only interested in estimating py. So reduced form is only interested in estimating py given 2x. This is the only thing I'm interested in. Right? So in order to estimate this, let's look at the graph like x and y. Let's find out what do I need to control, etc., etc. Okay? But after I do all these things, I only get this thing. That's the only thing I get, which is a discriminative method. But what structural does is to estimate x and y given, not conditional, but given a causal model, a theory model. So given a theory model, I'm going to estimate the entire joint distribution of xy. And in using this estimated model, I can do counterfactual simulations. Right? So that's the difference between, in causal inference, discriminative versus generative. One is reduced form, the other structural. And so in summary, the difference between structural and reduced form is two things. First of all, structural take theory seriously in the sense that the structural estimation uses economic theory to specify the functional form. Not just the graph, but also the functional form. The second difference is a structural estimation is typically a generative model, but the reduced form is typically a discriminative model. Okay, so they serve different purposes. In particular, structural estimation allows you to do counterfactual simulations. Okay. All right. Let's see. I'm already taking longer than I should. Final example. Okay. After that, I have to run. So far, all the models we have discussed are static. We haven't really touched dynamic models in this lecture, but dynamic models are extremely important, right? Now, in reality, in many times when you do economic analysis, especially when you're analyzing individual choices, economics is all about individual choice. But when an individual makes choices, is the individual making choice based only on today? No, right? The individual is making, when any individual makes choice, the individual, whether it's a company or a person or a government, it's always forward-looking. You are making choices while anticipating into the future. And this is very important, okay? So the ability to capture that forward-looking behavior is one of the most important things in many actual applications. But you can only do that with a dynamic model, not with a static model. Okay? Now, so a dynamic model is a model in which the environment is changing. And in every new period, there are some new information arriving, okay? So, and individuals in this kind of changing dynamic environment, first of all, are forward-looking. So when they're making decisions, they expect the future. That's the first feature of a dynamic model. The second feature of that model is your decision is also influenced by your past, in the sense that anytime you make your choices, you are confined by the constraints that are partly defined by the path you have already taken. It's like the Robert Frost point. Okay, so once you have once you have chosen the road, you cannot go back, right? So every decision you make, every path, every step you take is conditional on where you are, and you face the special constraint, right? So as an example, you guys are college students. So once you graduate, what do you do? Well, you may choose a graduate school or more graduate school and more graduate school, whatever, right? More graduate school, you can go work, and then when you go work, you can work in different industries. For every step you take, your future will be different, in the sense that your future choice will be different. Once you go on working for example, in the banking industry, probably it means that you cannot go to, let's say, legal industry very quickly, okay, as you wish. So every step you take, it changes the choice set you are going to face in the future. So anytime you make a choice, your choice depends on your past. Also, anytime you make a choice, you look into the future because you try to anticipate, expect, right? Because, for example, when you're making a decision about what you're going to do in the future once you graduate, you have to take into consideration that once I choose this path, I'm going to only have these options in the future. Once I take that path, I'm going to have a different set of options in the future. So when you make each choice, You always look into the future and try to calculate all the different paths available to you, conditional if you go here and go here, right? So in other words, in a dynamic environment, any choice is both forward-looking and also contingent on the past. Okay? The past defines the choice that you face today, and when you make choice today, you look into the future, and then on and on and on. This is a typical feature of a dynamic model. Okay? All right. In this kind of dynamic model, the static, if you disregard this kind of behavior, if you treat a dynamic model using a static model, then oftentimes you have a lot of bias as a result. Right? You see this kind of research all the time. So, for example, right, yesterday I went to a PhD thesis defense, I think the day before, and this kind of example everywhere. So, for example, a person is one of the research I see in the defense is this person estimate a model where it says, okay, this is the interest rate, right? So this is the interest rate set by the central bank, and for example, here is the leverage set by the bank, right? Leverage, right? Okay, so this person wants to know what is the effect of interest rate set by the central bank at t. How does the interest rate affect the leverage that financial firms take on? So the person do a linear regression where the interest rate is the interest rate of the central bank, maybe in t minus 1. Okay, so last quarter, the central bank sets a new interest rate. Let's see what happens to financial firms' leverage in this period, and then does a linear regression. Okay, beta 0 plus beta 1 plus some control values. What is the problem here? This is a static model, because this is saying that the leverage is determined in a static environment by the interest rate in the last period. There are at least several things wrong with this kind of approach. The main thing that's wrong with this approach is that when a bank sets its leverage, okay, when a financial firm decides how many debts do I want to take on, what is the leverage, the firm is always looking forward-looking, in the sense that the firm always anticipates what is going to be the future interest rate, right? Nobody make a decision based on last year's interest rate only. You're always trying to guess what's the interest rate going to be for the next 10 years, whenever you do any major decisions, right? Or whenever you change your leverage for them. So in other words, this leverage decision is not based on interest t minus 1 only, but based on interest what? Interest t plus 1, t plus 2, all the way in the future. And of course the anticipated, right? The expected interest. And all these expecting into the future determine the decision that people make today. If you disregard this forward-looking behavior and run a static linear regression, you are in for big trouble, right? Because your estimate is going to be severely biased as a result. Okay? So capturing forward-looking behavior is very important. The other thing that's wrong with this kind of model is that even if people are not forward-looking, so central bank sets a new interest rate, and it is going to affect the firm's leverage, but does it just affect leveraging the next quarter? In other words, is the effect immediately show up in the next quarter and never show up in the next quarter? No. It's going to slowly, in reality, any effect is going to slowly show up in the future, right? Slowly surface, because there's underlying mechanism in which the effect will slowly materialize. Okay? Because in reality, nothing immediately. The market oftentimes does not immediately clear, and the people does not immediately can go from state A to state B, because oftentimes it's costly and takes time for things to adjust. So there's a gradual process of the effect showing up. Right? So this kind of approach is wrong, at least for two reasons. The first reason is, in reality, the effect is often slow to show up because it's costly to transition from one state to the other. The second is people are forward-looking, so if you don't count that, you are in trouble. Okay? All right. So now let's take a look at how to actually do this. Right? So I critique this kind of approach. I say it's very bad. It doesn't give you the desired result. Now let me show you how to actually do a dynamic model. Right? How to actually take into consideration this kind of forward-looking behavior. Well, here's some data on farmer. Right? And this is what imagine there is a crop. Okay, the crop can be barley, I think. So this is the price of barley, which is a crop, over time. And this is how much farmers grow that crop. As you can see, that if we disregard the time dimension, if we only look at non-time dimension, like treat this as a static thing, okay? In a static framework, the higher the price, the more people cultivate. Pretty easy, right? So you can do a linear regression and you're done. But unfortunately, if you do a linear regression, you estimate the slope will tell you very little about what's actually going on. It's biased for the reason that I just described, right? Now, it's important actually to capture the dynamics here. The dynamics here is when the price go up, farmer, you see that farmer actually do grow more crop. But however, we are going to assume that first of all, farmers are forward-looking. So when I decide if I want to grow more crop, I'm looking not only at today's price, I anticipate the future price. Because in reality, farmer always have some information about where the future is going, right? So if I know that the future price is going to be higher, then I'm going to grow. If I see, so in this situation, when this year's price is high, but it doesn't really say about future, right? Because next year is going to be down again. So there's no growing trend, then I may not want to grow more this year. Why? Because it's actually costly for me to grow a crop and stop growing, and grow it again and stop growing again. Okay? So given this kind of cost, I'm not going to just react to a temporary increase and temporary decrease of price. But I'm going to react if there's a general increase in price for many periods. Because that makes sense now for me to actually try to grow a new crop or stop growing, right? So I'm going to build this all into my model. And in my model, so here's what the model looks like, right? At the beginning of each time period t, each farmer or each field owner is going to decide whether I want to grow a crop or not, okay? Whether I want to grow this crop or not. And when the farmer makes this decision, it is based on expectation of all the future prices. Okay? Now, if the future return is really good, I'm going to grow. If it's not good, I'm not going to grow. Specifically, what is the criteria that farmer use? The model assumes that once I go, if I'm currently not growing barley, but I'm going to start growing barley, there is going to be this so-called cost, this transition cost I'm going to pay. So this is a one-time cost, okay? So if I go from 0 to grow, I have to pay this one-time cost. In reality, that means right now you are not a barley farmer. If you have to start growing barley, there's a one-time investment cost, right? You have to purchase equipment, you have to purchase, fertilizers, everything, okay? So there's a one-time investment cost you have to pay. So in other words, if I see price go up today, but I'm not sure the price will continue to go up tomorrow, I'm not going to pay this one-time investment cost and start to grow barley. Okay? I'm going to wait. If I'm sure that, or if I anticipate future price to be high for many periods, then I'm going to make this one-time investment and become a barley farmer and start to grow barley. That's the idea behind this model. Okay? Now, once we do that, then I can estimate. What can I estimate? I can estimate the cost this farmer faces, and I can estimate other parameters like its utility and the preference parameters. And from those parameters, I can have this dynamic model. Right? So this red line will be the prediction of my dynamic model. Okay. Now you can say, why do you actually do this? Can I just use a time series to fit this? Yes, you can. You can use a time series to fit this data too. But the shortcoming of the time series model will be what? Will be just like the auction model. Once we change the environment, once you change the distribution, once we go up, more than go out of the range of the existing data, your time series model is not going to perform very well. But the model based on theory, if the theory is correct, will continue to perform very well if the distribution changes on magnitude, right? Okay. Now it turns out that we can also use the structural model to do counterfactual simulation. So here are two counterfactual simulations. The first simulation is I try to simulate what happens if people are actually myopic, meaning what happens if people are not looking into the future? What happens if people just simply make decisions based on today? Then if that's the case, then the response of crop to price changes would be much smaller actually, not as big. Okay? So my theory predicts that if people are not forward-looking, then the crop response will be much smaller than the observed response to price changes. Why? Very, very simple. The reason why we have this big response is because price has been high for many, many periods. So many people decide to pay the transition cost, pay the investment cost, and become a barley farmer. So this huge increase, right? Now, if people only care about today, they don't care about the future, then when I see this price go up, I may think about it, but next period is going down again, and next period is going up again, down again. In any single period, the increasing price is not enough to entice me to make the investment cost. So the response will be much smaller than before, right? So I can use, in other words, the myopic behavior will imply different kind of dynamics than a dynamic behavior. And I can predict that using my estimated theoretical model, which is also a kind of counterfactual simulation. Okay? All right. So that's all the example I want to give regarding structural estimation. Let me just say, okay, so one of the key things here I've sort of skipped over is that when I say in my model, I assume farmers expect the future. How mathematically, how do I actually do that? Right? In estimating my model, how do I actually assume that people look into the future? Well, it turns out that expectation is extremely hard to model. Now, so far, economists have no way of model estimation. So the basic strategy is to assume something called rational expectation, which is basically saying that the farmer's expectation of the future is sort of correct. Okay, so because we see in the data we see future price. There are two ways to model forward-looking behavior. The first way to model forward-looking is to say the farmers actually know the future price. That's called the perfect foresight. Okay, perfect foresight. Right? They know the future. The second way is to say they may not exactly predict the future price, but their expectation is basically the mean of future price. So in other words, they know the expected future price. That's called the rational expectation. Okay? So if you make this a kind of assumption, then you can model forward-looking behavior using dynamic model like this. All right? Okay. So that brings to the final thing I want to say today, which is I showed you 3 examples of structural estimation. And it looks like structural estimation is very powerful in the sense that if you use the theory, you can do counterfactual simulation, you can do very good out of range prediction, you can capture dynamic behavior, etc., etc. But all of these advantage builds on one simple core requirement, which is your model is good. Right? If your model is not good, if the auction model is wrong, if in reality people actually don't use that kind of strategy in reality, then the result you get is bad. Now, if in reality firms are not really maximizing profit and determining their pricing like what our model did, then that monopoly example, our prediction will also be bad. And in reality, if people do not have rational expectation, right, then this model is also going to be very bad. Right? So the validity of structural models depends strongly on the validity of the theory that you are actually using. If you use a very bad theory, then it's crap in and a crap out. Okay? There's nothing you can improve on that, right? So that's why, despite the obvious advantage of using structural modeling, despite that, the reduced form and the structural camp are continue to battle each other for this very reason. Structural people cannot guarantee that their model is good. In fact, in economics, most of our theoretical models are pretty bad. So because of that, the structural people really cannot show that their results really improve upon the reduced form people. And in fact, the reduced form people argue that by not using economic theory, especially to specify the functional form, their result is actually more robust because they are not beholden to misspecified economic theory. Okay, so that's why these two camps continue to battle each other. Each one has their valid points, and we don't have a very good solution so far. All right. Okay. So let's finish here today, and I really have to run.